The independent and dependent samples t-tests are the subjects of Chapter 18. So we'll begin with the independent samples t-test. So we've got two samples, not one, as was the case with the one sample t-test from Chapter 17. With one sample, the research question is, does the mean of a random sample differ significantly from some stated value? With two samples, the research question is, do the means of two random samples differ significantly from one another? So the key sampling distribution that we have been working with has been the sampling distribution of the mean. The sampling distribution that's important in the independent samples t-test is the sampling distribution of the difference between means. Now we're not going to go into the math or computations of this sampling distribution, but the key idea is that the means of two random samples can differ due to luck, chance, sampling error, randomness. I mean, all of these are the same thing. The two means can differ even when the populations from which each of these samples has been selected have equal means. So we're looking at, do the means of two samples differ by enough so that we can be confident that this difference isn't just due to chance. Hypothesis pairs can be either directional or non-directional. If you have a non-directional pair, you're going to have a two-tailed test. If you have a directional pair, you're going to have a one-tailed test. In words, the non-directional pair, two-tailed test, the mean of the population from which sample 1 has been selected equals the mean of the population from which sample 2 has been selected. And then the alternative would be the mean of the population from which sample 1 has been selected is not equal to the mean of the population from which sample 2 has been selected. Here is the non-directional pair expressed in symbols, and here are the directional pairs expressed in symbols. H1 is carrying the direction of expected results. The independent samples t-test assumes normality. It's robust to this assumption, so you're going to get sufficiently accurate results when the conditions described here are met. The n's here are pertaining to the sample size in each individual sample. So if both n's are greater than 10 and neither sample has strong skew, you'll get sufficiently accurate results. If n's are 20 or greater and you don't have extreme skew, results are sufficiently accurate. And when each sample size is about 60 or greater, then results will be accurate even when you have extreme skew. I'll mention that if skew is even more extreme than the extreme skew figure in Chapter 5, then in some situations sample sizes larger than 60 might be needed, but we're going to pragmatically adopt the guidelines that you see here. Another assumption of the t-test is the equality of variances assumption, also known as the homogeneity of variances assumption, and that is that variances are equal in the populations from which samples have been selected. And as you know, variance is a measure of variability. Variance is the standard deviation squared. So the notion here is we want our two populations to have equal variability. Now the robustness of the t-test to the equality of variances assumption depends on the n's. When sample sizes are equal or very nearly so, it is robust, this assumption. In other words, it yields accurate results even when the assumption isn't met. But when n's differ, results can be inaccurate. I mean, and that's particularly so if the n's differ by a considerable amount, and if the variances also differ by a considerable amount. Equality of variances assumption is tested by an equality of variances test, and the null hypothesis for that test is that the variance in population 1, sigma squared in population 1 equals sigma squared in population 2. You are not going to learn the specifics of an equality of variances test, and really in Chapter 18 we're going to be presuming that you have access to computer to carry out the independent samples and dependent samples t-tests. So, your computer package is going to carry out an appropriate equality of variances test. Now, if the computer package fails to reject the null hypothesis of equal population variances, so in other words, you don't get evidence that variances are not equal, in that situation, you're going to carry out an equal variances formula t-test. If the equality of variances test rejects the null of equal population variances, you are going to carry out an unequal variances formula t-test. I'll mention that there have been two formulas for several inferential procedures to this point, but the different formulas for each of these procedures have been alternative formulas that are mathematically equivalent and yield identical results. So that's not the case here with the equal variances formula and the unequal variances formula for the t-test. They will yield different results, so it's important that you conduct the correct one. Here are the degrees of freedom for the two formulas. Degrees of freedom are straightforward for the equal variances formula. The sample size in sample 1 plus the sample size in sample 2 minus 2. And for the unequal variances formula, this calculation is complex, and you don't need to learn this formula. Here is a general formula for t-tests with two samples, and this is the formula that we're going to use for both the independent samples t-test and the dependent samples t-test. The denominator of this formula is the estimate of the standard deviation of the sampling distribution of the difference between means. So you are going to be supplied with this estimate in all problem formulas that we do. When we did the one sample t-test, you were calculating the estimate of the standard error of the mean. You were dividing S, the sample standard deviation, by the square root of n to obtain that estimate. So we're simplifying things here, and I'm giving you the value of the estimate of the standard error of the difference between means. And the reason that you don't need to calculate this is that computer software packages will do this for you. So here's our calculation example, and as we get started on our calculation example, let me mention to you the independent samples t-test is one of the very most commonly used statistical tests. I mean, questions about whether means in two samples differ significantly come up much more often than does the question of whether a sample mean differs from a value. Very often experiments, for instance, will have two groups, and we want to compare the results in those two groups. So let me at least read the null. We're going to have a non-directional pair as we do our example. So the null, mean parent-child relationship scale score in the population from which respondents in one-parent families were randomly selected equals the mean score in the population from which respondents in two-parent families were selected. And the alternative simply states that these population means differ. We are going to use the 0.05 level. I'm going to be presenting results from the SPSS statistical software package, and it has a procedure for carrying out the independent samples t-test. And so at the top of this slide we see some descriptive information. For one-parent families, the mean relationship score is 3.46. For two-parent families, it's 3.32. And you can see the ends. Here there are more two-parent families, and here is the standard deviation of scores for each of these groups on the parent-child relationship scale. And I will mention to you that possible scores on this scale range from 1 to 4, with a score of 4 being the highest possible score, the closest possible relationship score that the scale can convey. Now, we're going to be carrying out the independent samples t-test, a statistical significance test, shortly. But one thing I want to encourage you to do when you work with data and as you begin to do statistical significance tests is not only to look at statistical significance, but also to take a look at size of association. So in Chapter 9 we encountered a basic tool, the standardized mean difference, for measuring size of association. The formula that we used in Chapter 9 provided an estimate. There's a precise formula in a footnote in Chapter 9. But let's just get an approximation, a feel for the approximate size of association expressed in standard deviation units between our two groups. So here are our two standard deviations. They don't differ by too much. We can get a pretty good estimate of our difference in standard deviations if we just take the average of these two. So the average standard deviation here is about 0.631. And so here is an approximation of the standardized mean difference. We'll take the mean in one-parent families, we'll subtract the mean in two-parent families, we'll divide by the approximate standard deviation in each group, and we get 0.226. So this is telling us that in our samples, the mean score in one-parent families is about 0.226 standard deviations than is the mean score in two-parent families. And were we to page back to Chapter 9, you could see that 0.20 standard deviations was our qualitative descriptive guide for small association or small difference. So as we look at this data, it's going to be helpful to us to see that this is a reasonably small relationship. That provides us with some good guidance as we move forward into the significance test, which is to say the independent samples t. So here is some information that SPSS has presented for us pertaining to the equality of variances assumption. It carries out something called Levene's test, and we don't need to go over the specifics for that, but here is the result for Levene's test, and importantly, significance. And significance conveys p, or p-value. The significance is 0.12. So Levene's test is failing to reject the null of equal population variances. So we don't have strong evidence that the population variances aren't equal. Therefore, We'll presume that they are equal, and as we have failed to reject the null equal population variances, we're going to use the equal variances formula for our t-test. Okay, we've got lots of information on this slide. I mean, here's our t-test formula. So we failed to reject the null, hence we want to make use of the t-test results for the equal variances formula. Here are those results. Here are the results for the unequal variances formula. Over here is the standard error of the difference as labeled by SPSS. This is the estimate of the denominator here, the estimate of the standard error of the difference between means. What does this mean difference here of 0.142? I mean, there's some rounding error involved, but basically it's the subtraction of 3.317 from 3.46, and we get 0.142. Here is our calculation of t. So the mean in the first group, subtracting the mean in the second group, dividing by the standard error of the difference between means. That is 0.143. Again, there's some rounding, divided by 0.066, and 0.143 divided by 0.066 equals 2.166. So that's the value of t. Here are degrees of freedom in the equal variances test, 745. Where is that coming from? Well, the sample size in the first sample is 114, that in the second is 633, and so degrees of freedom formula is presented N1 plus N2 minus 2, so 114 cases in the first sample plus 633 in the second sample, subtract 2 yields 745 degrees of freedom. Now, SPSS oftentimes conveys p or p-value with SIG, short for significance. So the significance or p-value for the equal variances formula comes out to be 0.031. In other words, given a true null, you obtain results that differ by as much as do the results in these samples in 3% of random samples. So to speak, there is a 3% chance that this difference is due to simply to the luck of the draw of samples. But indeed, our p-value 0.031 is less than the value of p that's connected with our selected significance level. It's less than 0.05, and so therefore we reject the null. And as you know, whenever the null is rejected, automatically the decision gets made on the alternative, and it's the opposite decision, so we are going to accept the alternative hypothesis. Value of p is indeed less than 0.05. That's conveying to us that the difference in mean closeness scores in the two groups is unlikely to be due to chance alone. There's a 3% chance of obtaining these results or more extreme results given a true null. Less than 0.05, we reject the null. Now, computer software package results convey exact probabilities. In other words, the exact probability that the result is due to chance alone was 0.031. On the other hand, tables, such as those that we're using in the text, convey whether the probability of the study sample result is greater than or less than the selected significant level. So tables aren't going to tell you the precise probability. They're simply going to tell you whether the probability is greater than or less than the selected level, in our case 0.05. Recall that we had 745 degrees of freedom. Oftentimes, a t-test table does not list the precise degrees of freedom that are associated with a given t-test. Now, if you're using a table, what you need to do if the precise degrees of freedom aren't listed is to use the next smaller row. So in our table at the back of the text, 745 is not listed. The closest smaller number of degrees of freedom is found in the row listing 500 degrees of freedom. So we're sticking with the 0.05 level, which is to say alpha equals 0.05. And for 500 degrees of freedom, the tabled value of t is 1.965. That's in essence our critical value of t. So the obtained t is 2.166. The absolute value of 2.16 is indeed 2.166. 2.166 is greater than 1.965, and hence we reject the null. So if you use tables, you'll reach the same decision as you reach with the computer packages. You just don't learn the exact probability of the study result.